The last topic in this chapter is binomial and geometric random variables. They're related, and as the title says, these are special types of discrete distributions. So discrete, again, being numeric variables that take on specific values on a number line. In this case, we're going to be taking on natural numbers or whole numbers. So this video is going to talk about binomial variables, and then later we will talk about discrete. So in this video, we're going to talk about conditions for a binomial distribution. We're going to identify binomial distributions, and then we're going to calculate some probabilities. So you will need a calculator. First thing I want to talk about is what are the conditions for a binomial setting. So there's an acronym that you need to remember. Any binomial setting is always going to have the same 4 conditions. The acronym is BINS. So the B stands for binary. What I mean by that is in a binomial setting, there's either success or failure. So there's no other options. I stands for independent. What I mean by this is that the trials need to be independent. So one trial is independent of the next. Whatever happened in this trial doesn't affect the next one. N stands for number. I know that's not very specific. What I mean by that is a fixed number of trials. And S stands for success. What I mean by this is that the probability of success is constant. So the probability of success in the first trial is going to be the same as the probability of success in any other trial. So what is a binomial random variable? A binomial random variable counts the number of successes in n trials. What are the possible values? They have to be discrete. So we can have 0 successes, 1 success, 2 successes, all the way up to n successes. So those are the only possible values that a binomial variable can take on. So we would never say that a binomial variable takes on the value 1.5. You can't have 1.5 successes. So the parameters for a binomial distribution, there are 2 parameters. N is the number of trials. So by parameters, I mean how do we define the distribution? So a binomial distribution is defined by the number of trials, and then P is the probability of success. Okay, this should be similar to a normal distribution. So in a normal distribution, you always have to define mu and sigma, so you always have to give the mean and the standard deviation. Those are the parameters for a normal distribution. So for a binomial distribution, the parameters are n and p. What is the most common mistake students make on binomial distribution questions? The biggest mistake that I would say is that students don't even recognize that the distribution is binomial. So you will never be told that a distribution is binomial. You'll need to be able to recognize it. So similar to when we did tree diagrams, sometimes you all had problems recognizing when something was a tree. You're going to have probably the same issues with binomial distribution. So we're going to start just by looking at a few examples and determining if they're binomial or not. So again, something is binomial if it follows the 4 conditions, the BINs that we did above. Okay, so determine whether the random variables below have a binomial distribution and justify your answer. So in part A, we are rolling a fair die 4 times, and x is the number of 6s. Okay, so we need to ask ourselves, is this binary? Do we have success and failure? In this case, success is a 6. Failure is anything that's not a 6. So that works. Are the trials independent? So when I roll a die, is that independent of the next roll? Well, yes, that is. Is there a fixed number of trials? Yes, I'm rolling 4 times. And then does the probability of success stay the same? So the probability that I roll a 6 on my first roll, is that the same as my second roll, my third roll, my fourth roll? Yes, it is. So in this case, we say that x is binomial. So if you remember, this is the notation from a normal distribution. It means you're defining your distribution. N, so the number of trials is 4. P, my probability of success in this case, is 1/6. So that's the probability of rolling a 6. Okay, so part B. You shoot a basketball 20 times from various distances on the court. Y is the number of shots made. So we want to know, is Y binomial, yes or no? So first of all, is this binary? Do I have success or failure? Well, yes, I do. Success in this case is that you make the shot. Failure is that you miss. Then I need to know, are these trials independent? We're going to say maybe. I would argue probably not. If I'm shooting a basketball, it's reasonable to believe that the more I shoot, the better I get, or maybe I get more tired, so probably not independent. Is there a fixed number of trials? Well, yes, I'm shooting 20 times. Is my probability of success the same? No, it is not. So again, the more I shoot, I might get better, I might get more tired. It also says from various distances. So the closer I am, maybe I'm more likely to make the shot than further away that I am. So part B, this is not binomial. Part C, observe the next 100 cars that go by and let C equal color. So is this binomial? No. Is this binary? No, it is not. So if I'm looking at color, there's more than 2 different colors. Furthermore, this is not discrete. It's not numeric data. So this would not be binomial. So now that we are able to identify binomial, we also need to be able to calculate probabilities using binomial distributions. So that's what we're going to do on the next page. Okay, so in many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1/6. If x is the number of 6s in 4 rolls of a fair die, x is binomial with n equals 4 and p equals 1/6. So this we already talked about. That was on the previous page. So when it says, what is the probability that x equals 0? Okay, so x being the number of 6s. So I'm really asking, what's the probability that all 4 rolls are not 6s? Well, the probability of not being a 6, so this is really the probability of 4 failures. The probability of not being a 6th is 5/6. But then I'm rolling the dice 4 times, or the die 4 times. So that's 5/6 to the 4th, which is about 0.482. Now, why am I able to take 5/6 to the 4th? Well, I know that each roll is independent. So that goes back to probability. Okay, so now this one is a little bit different. What is the probability that x equals 1? That means that you roll 1/6. So you have 1 success and 3 failures. Well, that happens a few different ways. I could have my first success and then 3 failures. The success could be the second roll. The success could be the third roll. Or the success could be the last roll. So when the probability that x equals 1, I need to take into account all 4 of those probabilities. Now, they're all going to be the same. So the 1 success is 1/6. That's for rolling a 6. The 3 failures are 5/6. So that's for my 3 failures, but I have to cube it. Then, because there are 4 different options, I have to multiply by 4. Okay, so this ends up being about 0.386. Okay, so then what about probability of 2, 3, or 4? These are going to be similar ideas. 2 means I have 2 successes. Well, they could be the first 2, they could be the middle 2, or any other combination. So I believe that's all of them. So our probability that x equals 2 then would be 1/6 squared for my 2 successes. 5/6 squared for the 2 failures, multiplying by 4 because there's 4 different cases. So if you were finding the probability that x equals 3 or x equals 4, it would be the same idea. Now, there is a formula. You're not just going to have to write out all the possibilities every time, but we did this so that we can come up with what the formula is, and so that the formula makes a little bit more sense to us. Let's see, we want the probability of x equals some number of successes. Well, something's going to go there. Now, if we look back up to the probability of x equals 2, that 1/6 squared was for the number of successes. So this is going to be p to the k if we have k successes. Everything else is a failure. So if p is the probability of success, 1 minus p will be the probability of failure. If I have k successes, the rest of them are failures, so that's n minus k. And then what you noticed is we always had to multiply by how many different cases there were, which happen to be 4 and 4. They're not always going to be the same. The way you find out how many different possibilities there are, so how many ways you get a certain number of successes, is n choose k. So I'm going to show you how to do that on the calculator. It's not a fraction. That's read n choose k. So this is the formula. Is it on the formula sheet? Yes, it is. You guys aren't using the formula sheet yet, but that eventually will help you. So we're going to do an example together, and I'm going to show you how to do this on the calculator. In roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of a roulette wheel. So first of all, part A, what is the probability that exactly 4 of the spins land on black? So first we need to ask ourselves, is this binomial? Do we have a binary variable? Yes, we do, either black or not black. Are the trials independent? Yes, if I spin the roulette wheel, that has no effect on the next spins. Do I have a fixed number of trials? Yes, there's 10 different spins. And then does my probability of success stay the same? Yes, if I spin, whether or not I get a black is going to be the same for every spin. So the first thing that we're going to do is we need to define a variable. So I'm going to use x. You need to tell me what x means in context. So x is going to be the number of times that we land on a black space. Okay, so then x is binomial. Our n in this case, so our number of spins is 10. P, our probability of success. Again, success in this case is spinning a black space, is 18 out of 38. So part A, what is the probability that exactly 4 of the spins land on black? So I'm looking for the probability that x equals 4. Okay, so using our above formula, n in this case is 10. I'm looking for 4 successes. My probability of success is 18 out of 38 to the 4th power. Probability of failure then is 1 minus 18 out of 38 to the 6th power. Now this should make sense. Again, this is all of your successes. This is your failures. This is how many combinations there are. So what I want to do right now is show us how to do this on the calculator. So if you could take your calculator out. Okay, so first thing that you're going to need to do is you're going to need to type in that 10 choose 4. So you're going to type in 10, then you're going to go to math and over to probability, and you're going to choose number 3. Then you can put in the 4. Now, at this point, mind you, yours might not look exactly the way mine does based on what version of the calculator you have and what software, which is fine. Still follow along. End your parentheses, and then you're going to type in the rest like you normally would. So the 18 over 38 to the 4th power, again for your 4 successes, and then the 1 minus 18 over 38 to the 6th. So our answer ends up being about 0.225. Okay, so if you didn't catch that, you're going to need to rewind the video and rewatch the calculator part. So this is exactly all of the work that I expect to see when you do a binomial problem. I want to see you define the variable. I want to see you put it in probability notation. I want to see the formula, and then I want to see an answer. So if we do B now, what is the probability that at least 8 of the spins land on black? So I want the probability that x is greater than or equal to 8. So in this case, you're going to have to calculate the probability that x equals 8, probability that x equals 9, and the probability that x equals 10. So I don't expect to see the formula 3 times. If you show it to me once, like you already did in part A, that's enough, and now you can just go to the calculator. So if you want to pause the video and take a minute to try that, I will tell you that this probability ends up being about 0.038. Okay. Now, what's lucky for you is that there's a faster way to do this on the calculator. So what I just showed you is the long way, but I wanted to show you how to use this formula. So what we're going to do next is we're going to look at the quicker way to do this on the calculator. Okay, so on the calculator, you're going to go to where normal CDF is and normal PDF, although we don't ever use that. And if you scroll down, there's going to be 2 different functions. There's going to be binom PDF, and there's also going to be binom CDF. Okay, in either one, you're always going to put n, so the number of trials, p, the probability of success, and then you're going to put k, which is your number of successes. Now, here's the difference for p versus c. C is for cumulative probabilities. So when you use CDF, it's going to tell you the probability of that k value and everything lower. PDF is just one specific point. So I'm going to show you how to do all of these on the calculator. If we look at x is the number of heads and 50 flips, we need to find the following. So we're going to say x is binomial. And in this case is 50 flips. Probability of success is a head, so that's going to be 1/2. So if we were using the formula like we did before, this would be 50, choose 25 successes. I have 1/2 to the 25 for all the 25 successes, and then I have 1/2 to the 25 for the 25 failures. Now, you could certainly do that this way, but if you want to, again, keep your calculator out, I'm going to show you a quicker way to do this. Okay, so again on the calculator, you're going to go second distribution, which is where you find normal CDF, and you're going to scroll down until you hit normal PDF. Now, yours might not look like this, and if that's okay, that's fine. You still need to give the same information, you're just going to put a comma instead. So there are 50 trials. P is the probability of success, so again, that's 0.5, 1/2. X value is the number of successes. You're going to hit paste, and then you're going to hit enter. So this is the probability of 25 heads. So in terms of my expectations are the same as they were earlier in the video. You need to define x in terms of the context. You need to define the distribution. You need to show me the formula, and then you can use the calculator. So I always expect to see the formula in a single probability. As soon as it's cumulative, you don't need to show me a formula anymore. So if we were planning to use the formula here to find the probability that x is less than or equal to 18, what we would have to do is we would have to find the probability that x equals 0 all the way up to 18, which is not very efficient. So what we're going to do is we're going to use the calculator. Again, binom CDF is a cumulative probability. So what we're going to put in is we're going to put in our calculator in a minute, binom CDF of 50 trials, 1/2 is still my probability of success, and then I'm going to put in 18. And using the CDF, we'll calculate the probability of 18 and below. Okay, so we're going to go back to the second distribution and scroll down again, but now you're going to choose binom CDF instead. All the same information you're going to put in. So the 50, the 0.5, the 18, and then you're going to hit paste. Okay, so that's the probability of at most 18 heads. Okay, so again, it's really important we know when to use PDF and CDF. PDF is a single probability. CDF is the probability of that point and everything below it. So we're going to see one more example of how to use the CDF, and then we're going to finish the rest of the notes. What happens if I ask you for the probability that x is greater than 30? Well, if I use PDF, I could calculate 31 all the way to 50 successes, which is not very efficient. Is there any way that I can use CDF? Well, CDF is cumulative, but it's that point and everything below it. So in this case, what we're going to do is we're going to calculate the complement. So I'm going to take 1 and subtract the probability. Okay, so if I want 31 and up, that means I need to subtract at most 30. So if I subtract x's 0 to 30, that leaves me 31 to 50. So in this case, again, on the calculator, you're going to do binom CDF of 50 trials, probability of success is 1/2, comma 30. Once you do that, you're going to subtract your answer from 1, and that would give you the probability that x is greater than 30. Okay. Just a few more things to talk about, and then we're going to be done. Is it okay to use binom PDF and binom CDF on the AP exam? Absolutely not. So what I have up above, that should never be on the AP exam. This should never be on the AP exam. What I do want on the AP exam is define your variable, show me a formula. Those two I want. Do not ever put calculator commands on the AP test. Now, again, if you are looking for multiple probabilities, you don't need to show a formula. I only want you to show a formula when you are finding a single probability. Last thing we need to talk about is how do you calculate mean and standard deviation of a binomial distribution. Like any distribution, you're always going to be interested in the mean and the standard deviation. The mean is going to be n times p. Standard deviation is the square root of n times p times 1 minus p. Are these on the formula sheet? Yes, of course they are. So last thing we need to do is we need to talk about finding a few, and then we actually do have one other thing to talk about. Let x equal the number of the next 10 spins of a roulette wheel that land on black, where the probability of black is 18 over 38. Calculate and interpret the mean and standard deviation. Okay, so if I'm finding the mean, it's going to be n times p, always show a formula. N in this case is 10, p is 18 out of 38. So our mean in this case is going to be about 4.74. 4.74, interpreting, that's going to be the expected number of black spins, or spins on a black tile, out of 10 spins. Now, I don't want you to round that. Doesn't make sense to round that. Or it would make sense to round that. You can't have 4.74 spins, but like we normally do, you're not going to round it. If we want to find the standard deviation, n is going to be 10. Probability of black is 18 out of 38. And then we also have 1 minus p. So if I calculate this, it ends up being about 1.58. Okay, so then again, what does this mean? This means that the number of spins that land on black will typically vary by 1.58 spins from the mean. Okay, so there's still a little bit left with binomial distributions, but what we've done right now, that's the bulk. So there's a little bit of notes left that we can either take tomorrow or after break or at some later point in time. But when you come to class tomorrow, I'm going to expect a few things of you. One, that you know what the conditions are for a binomial distribution. 2, that you can identify a binomial distribution. 3, that you can calculate the mean and the standard deviation. And lastly, I'm going to expect you to be able to calculate probabilities of a binomial distribution using your calculator and the formula. If you have any questions, I would be happy to answer them in class tomorrow.